Welcome to Chapter 1 of our module on Artificial Intelligence. I am Dr. Alaa Jabbar Almaliki from the School of Computing at Universiti Utara Malaysia. We describe AI as science fiction, but reality is grounded in mathematics. Building it requires translating biological cognition into a reproducible algorithmic workflow. In this session, we will outline our foundational learning objectives. We will define natural intelligence, contrast it with machine intelligence, and map the historical development of these systems to understand the current state of the art. Traditional computer programs execute rigid, predefined instructions. Modern artificial intelligence analyzes data, recognizes mathematical patterns, and dynamically adapts to situations with minimal intervention. But before we can engineer systems capable of machine learning or deep neural networking, we have to establish a strict baseline. We must first deconstruct the biological definition of intelligence itself. Natural intelligence, or NI, is the biological capability of living organisms, primarily humans, to acquire knowledge, solve complex problems, apply logical reasoning, and adapt to changing environments. This intelligence relies on a network of cognitive abilities: learning, reasoning, perception, memory, decision-making, creativity, adaptability, emotional intelligence, and common sense. The brain executes a continuous learning loop. We process sensory input, compare it against stored memory, and apply that synthesis to inform decisions. This biological system is efficient. Humans can generalize knowledge from limited data, exercise nuanced ethical judgment, and utilize empathy to navigate complex social relationships. However, natural intelligence is bound by biological constraints. Humans require rest, our memory capacity is finite, and our cognitive performance fluctuates due to fatigue and emotion. When we attempt to replicate these cognitive abilities in machines, we have to translate the biological brain into computer hardware and algorithms. This comparison table shows the structural differences between natural and artificial intelligence. The divergence begins with how each system acquires knowledge. Humans learn through lived experience and observation, while an AI model depends on training data and programmed algorithms. Because machines learn through statistical patterns, they possess a deficit in intuition. They lack genuine consciousness, empathy, and the practical common sense that humans apply to everyday situations. Human adaptability is an intrinsic survival mechanism. A machine's adaptability is strictly bounded by its original design and requires explicit retraining to handle environments outside its initial parameters. But machines hold a distinct advantage in processing capacity. While biological brains are slow at numerical calculations and require sleep, artificial systems process massive datasets and operate continuously. This highlights a technical distinction. High computational speed is not the same as intelligence. True intelligence requires the ability to reason, solve unfamiliar problems, and adapt. Therefore, modern artificial intelligence is not a mechanical replica of the human mind. It is a highly specialized engineering tool designed to execute logic and process data at scales that bypass our biological limits. John McCarthy officially coined the term artificial intelligence in 1956. He defined it as the science and engineering of making intelligent machines, especially intelligent computer programs. That pursuit began with massive hardware, where early engineers manually wired cabinets to automate complex mathematical logic. Today, engineering a modern AI system requires the integration of 5 interdependent technical components: data, algorithms, a learning model, computing power, and evaluation. High-quality data acts as the absolute foundation of the system. The algorithms then provide the processing logic, defining exactly how the machine will parse that information. The mathematical learning model maps the relationships within the data to predict future outcomes. Running these vast matrices requires immense computing power, driving the demand for specialized hardware like modern CPUs, GPUs, and TPUs. Finally, during the evaluation phase, engineers apply strict performance metrics to measure the system's accuracy and reliability, ensuring it behaves correctly before it is allowed to interact with the real world. Without the seamless integration of all 5 structural pillars, artificial intelligence remains dormant data and unexecuted code. To see how these components interact in practice, we can map the standard 6-step cyclical workflow that dictates how most machine learning applications operate. The cycle begins with data collection, gathering massive volumes of relevant information. Step 2 is pre-processing, a cleanup phase where engineers remove errors and inconsistencies so the machine receives a clear mathematical signal. Step 3 is model training. This is where the algorithmic model begins identifying statistical patterns and relationships hidden within the clean data. In Step 4, the model undergoes testing. It is evaluated against unseen data to measure its performance and ensure it hasn't simply memorized its training set. Step 5 is deployment into real-world applications. Step 6 establishes a loop of continuous learning, updating and retraining the system as new data arrives to maintain accuracy over time. From the machine's perspective, this process looks like an endless stream of geometry and probability matrices, updating bounding boxes and predicting vectors for every moving object in its field of view. Effective learning in this context requires a relentless, ongoing cycle of mathematical refinement. Based on their cognitive capabilities, we classify these systems into 3 major categories. First is artificial narrow intelligence, or ANI. These systems are highly specialized to perform one specific task. Almost every AI application used today exists entirely within this weak AI category. The second category is artificial general intelligence, the pursuit of machines capable of human-level reasoning across multiple domains. Beyond that is artificial superintelligence, a theoretical concept describing a system that surpasses human cognitive ability. Despite being narrow, ANI offers industrial advantages. These systems process enormous datasets and execute complex, repetitive physical tasks with precision, continuously operating without fatigue. However, deploying these systems involve limitations. They require immense computational infrastructure costs. Furthermore, they are literal, operating without empathy or situational common sense. There is also an ethical vulnerability in their data dependency. If the training data contains human biases, the machine learning model will inherit, replicate, and scale those biases into its decision-making logic. An AI system's greatest asset is its rigid adherence to data patterns, yet that rigidity is simultaneously a dangerous vulnerability, making strict human oversight an absolute requirement. Today, these theoretical architectures manifest as tangible technologies. Spatial AI and predictive algorithms manage global logistics, allowing autonomous vehicles to navigate active traffic by interpreting continuous sensor data. In cybersecurity, machine perception systems analyze biometrics. Algorithms map the exact geometry of a human face to verify identities and detect unauthorized intrusions. Natural language processing models allow consumer-facing virtual assistants to parse spoken human language, accurately interpret user intent, and execute tasks on demand. These language models facilitate cross-cultural communication, providing instantaneous text and audio translation between different linguistic structures. Artificial intelligence has evolved from a theoretical computer science challenge into a constant presence in modern human society. As we project the evolution of this technology, researchers anticipate breakthroughs in autonomous scientific discovery and the integration of collaborative AI systems working alongside humans. But this rapid evolution carries an ethical burden. It is the responsibility of future developers to enforce algorithmic transparency, ensure fairness, and mandate strict privacy controls. To summarize, artificial intelligence seeks to replicate biological cognitive tasks through engineered, data-driven systems. While our current society relies on narrow intelligence, understanding these architectural pipelines is the necessary stepping stone toward achieving general intelligence. That concludes Chapter 1. Remember, mastering these architectural pipelines requires understanding both the mathematics of the machine and the philosophy of the human mind.